Hello. So today we're gonna do the common-emitter amplifier. This is gonna be part 2. So we are mostly gonna be interested in the AC part of it. So in the previous video, we did the DC analysis and we were able to get to compute RC, RE, R1, R2. So our next task is to figure out the value for R3, the resistance in that bypassing branch. So C2 is the bypass capacitor. And when you do DC, you don't consider that branch, but when you do AC, you obviously have to consider it because the capacitor is passing the current. Okay, so let's figure out how to compute R3. Quick change of board. So let me redraw the part of interest. So you have the transistor, emitter branch here. So let's put the RTR or RE, which is the transresistance. And this is, so RTR is equal to 26 millivolts divided by IE, and this is DC current. So it's 26 millivolt divided by IC. So in our case, the assumption is that IC equal 1 milliamp. It gives you a 26 ohm value. Okay, so that's the RTR. And it goes into RE, and then the bypassing branch R3, and the capacitor, which is C2. And that goes to ground. Okay, so when you have AC, C2 is gone. It's just a short. So that's your situation. So to get R3, we need to use the gain. So we have gain. Oops. Gain equal to minus. No. Gain is equal to minus 100. That's your assumption. Okay, so that's your assumption. And so the definition of gain is small v, small c. This indicates AC. Small v, small c over small v, small b. So the collector voltage over the base voltage. So we're going to use that to compute R3. So let's get VB. VB, so this is the emitter and this is the base. So this is the emitter. I should have put it here. So if you do DC, you know that VB is 0.6 volt higher than VE. But if you, in AC, VB is equal to VE, only in AC. So small v, small b equals small v, small e. So let's compute. So VB equal VE is equal to, so it's going to be RTR plus RE in parallel with R3 Okay, so and here there is a IE, small I, small e, the current, the AC current in the emitter leg. So RTR plus RE parallel to R3, IE. So we know that the gain is VC over VB equal VC over VE. And what is VC? We need to express VC. Of course, the small IE here is IC. So we need to express, so V, we're going to put it here, and we would like to get rid of that IE, IC. So we need to express VC as a function of IC. So how do you do that? Let me get the next board. It's pretty easy. So we want we want VC, small v, small c. So AC voltage at the collector. So easy, it's easy. So VCC RC. So here I'm just doing the collector leg. Okay, so that's the collector. So here you have IC, big I, capital C, and you have small I, small c. So this is DC, and this is the AC part. And this is, of course, RC, the resistance in the collector, and that's the source voltage. So just use KVL. So VCC is equal to RC times IC, big C plus small I, small c, plus VC, big cap C, so that's DC, plus VC. So this is DC, this is AC, this is AC. But we know that if you look at just the DC stuff, VCC equal R. So you do KVL in the DC analysis. So VCC equal RCIC plus VC. So this is all DC. So what happened is that this is gone, this is gone, and this is gone. So you end up with 0 equal RCIC plus VC. So this is all AC. So you end up with VC equal minus RCIC. Okay, so we're going to plug that into the other board. So VC, we just computed VC equal where can I put it? We just computed, I put it here. So VC equal minus RCIC. So this is all AC stuff. So minus RCIC divided by VE, which is here. So RTR plus RE parallel to R3 times IE, which is equal to IC. So this is gone, this is gone. So you end up with gain, which we know is minus 100. RC, we know what it is. It's 10K. RTR, we know what it, RTR, we know what it is. RE, we know what it is, and R3 is the only unknown. So it gives us R3 is equal to minus RC divided by the gain, minus RC divided by the gain, minus RTR. So it gives us 10K divided by 100 minus 26. It gives you 74. It gives you 74 ohms for R3. So, but this is the equation for R3. That's the one, the important one. Okay, so that gives us R3. So what's next? What's next is the capacitors. The capacitors, we have to do that. So we just got R3. So let's compute C1. Okay, so let's redraw that circuit. This is the circuit. But because we are doing AC analysis, VCC is actually a ground. VCC is a ground, so it's a constant voltage source. So in AC analysis, it becomes a ground. So we can redraw this thing. So this is the input. Here. Then you have the C1. So then you have to ground R1. Then you have the other one, R2, to ground. And then you go into the base. So then you have RC up here. Also to ground, because it connects to VCC. So this is the ground. On the emitter, this is collector. Emitter side, we have RTR, RE, ground. And then you have the bypass. So you have the R3, capacitor, and the ground. So this is the C2. Okay, so let's go back. Here, R1 goes to VCC. In AC analysis, this becomes ground. R2 goes to ground. On the collector side, RC goes to VCC, but in AC analysis, it goes to ground. And then we have this. But here I'm adding the RTR on the emitter leg. So this, okay. So this is AC always. So what is C1? To compute it, you have to look at this as a high-pass filter. So high-pass filter, it lets go through the higher frequencies. I mean, past the cutoff. So it looks like this. So that's your capacitor, and you have a resistance here, and that's the other rail. Okay, so that would be the plus, that would be the minus, plus minus. So the cutoff frequency, Fc, is equal to 1 over 2 pi R. So this high-pass filter lets frequency higher than this go through, basically. So this is called the cutoff, or the corner. Sometimes it's called corner frec. So we're gonna use that. We're gonna use that because we know the assumption is that Fc is equal to F3 dB, and it's equal to 100 Hertz. So F3 dB means that the 3 dB means you lose half the power. So it's 100 Hertz. That's an assumption that is made. So what is the... Okay, so C1 is equal to 1 over 2 pi F3 dB times R in. So the R is called R in. Or I shouldn't say R in. It's R in is like the resistance looking here. This is the R in. It's the resistance looking this way at this point. R in. And so R in, what is R in our case? So you have R1 in parallel with R2. Okay, R1 in parallel with R2. And then you have this resistance here looking into the base. So plus R in base AC. That's what they call it in the practical electronics for inventor's book. It's this resistance looking into the base. So this R in base AC, R in base AC, the only way you can get it is that you have to compute VB over IB. Okay, because here the transistor is an active component, it's not passive, so you have to use the ratio VB over IB. So VB is the AC voltage at the base and IB is the AC current at the base, through the base. But we know that small VB is equal to small VE. IB stays the same. And the small VE we did compute it before. Yeah, we computed it before when we were getting the value for R3. Okay, VB equal RTR plus IE in parallel with R3 times IE or IC. Okay, so it's RTR plus RE parallel with R3 times IE divided by IB. This is IC, that is it's beta IB, so IB gets cancelled, and you end up with R in base AC is equal to RTR plus RE in parallel with R3 times beta. Okay, so what you can do is you can assume that RE, the value of RE is much greater than R3, which is true. RE is much greater than R3. It means that in a parallel setup, you can get rid of the RE. So this is just R3. So R in base AC is equal to RTR plus R3 times beta. I should have put it here. So it is equal. So R in this formula, R in base AC is equal to beta times RTR plus R3. Okay. So RTR we know it's RTR is 26, R3 is 74, beta is 100. So we know R in base AC, and then you just have also to plug in the R1 in parallel with R2. So we know that also. So you can get the R in. So R in is 5K ohms. And this formula C1 equal 1 over 2 pi f 3 dB R in F3 dB is 100 Hertz, it gives you a C1 equal 0.32 microfarad. Okay, so C1 is equal to this. Okay, so we are done with C1. So the only one left is computing C2. So let's go back to this guy. So now we just got C1. Now we just need to compute the C2, the bypass capacitor. Okay, so C2. Okay, so let me redraw again. So you have the collector, emitter, base, emitter, RTR, and here you have RE, and on this branch you have R3 and the C2, and that goes to ground. That goes to ground. So again, we have a high pass filter. This one is a bit harder to see because you have to consider the current going this way instead of that way. So it goes this way. Okay, so again, and we know that Fc equal 1 over 2 pi Rc. So this is the cutoff frequency or corner frequency. So ours is going to be Fc equal F3 dB equal 100 Hertz. So we only pass stuff above 100 Hertz. So C is equal to 1 over 2 pi Rf, where F is the F3 dB at 100 Hertz. And the R, so the R is basically the resistance looking in here. So I'm going to call it R in. R in times F. So this is R in. So it's the resistance looking in. Okay. So what is R in? So R in is equal to you have R3 plus RE, and RE is in parallel with RTR. Why is that? Because RTR, like there's a constant voltage source here between B and E, so it's like a ground here. In AC analysis, here it's like a ground. It's like a ground here. So RE is in parallel with RTR. So this is the R in, and because RE is much greater than RTR, which is true, R in is equal to R3 plus RTR. Okay, so RE is much greater than RTR, so you can just, because this is a parallel setup, you can just get rid of RE, and you end up with R in equal R3 plus RTR. So that gives you C2 here. So C2 equal 1 over 2 pi R3 plus RTR times F3 dB. So we know everything here. This is 74, this is 26, this is 100. It gives you 16 microfarad. Okay, but that's the formula here. C2 equal this. That's your formula for the bypassing capacitor. Okay, so that's it. So if you go back to the initial circuit, in the previous video we computed RC, RE, R1, R2, and in this video we just computed R3, the resistance in the bypassing branch, C1, okay, the capacitor at the input, and C2, the bypass capacitor. So we are done here. So if you like this kind of content, please like, comment, subscribe. It really helps the channel. And let me know if you want me to make more. I will probably make more anyway. So see you around. Bye.